I thank you for the invitation. My apologies that I couldn't be there in person this week. I was hosting a visitor here at Berkeley, but thanks for accommodating me as a virtual talk. So I'm going to talk about private frequency estimation. This is joint work with Vitaly Feldman, Hui Nguyen, and Kunal Talwar, and it's related to problems that we've seen in massive data algorithms like the heavy hitters problem in the streaming model, for example. So what's the problem that we're looking at today in this talk? So I have a smartphone. I imagine many of you in the audience also have smartphones, and we rely on certain nice features that these devices provide. For example, autocomplete when you're texting your friend, or also automatic spell correction. And how do these things work? Well, I don't know all the details, but they're using machine learning, which means they have some ML models, and they need to train those ML models, right? And here's a patent from Apple, for example, that's directly related to this for learning new words. Basically, people are texting their friends and they want to learn words from the text. So, you need data to train the ML models. Where's the data coming from? The data is coming from us, right? Us, the users of these smartphones. Learning new words generated by user client devices in a crowdsourced manner. Okay, so that's basically learning from our data. So the setup is you have a bunch of devices, n devices. Each one has, say, the last word that was texted to their friend on their device. And the server, which in this case is the creator of the smartphone, Apple or Google or whoever, they want to know things about the distribution of data. For example, the word distribution amongst devices, the frequency of word X. F sub X is how many devices just texted the word X. So this is some histogram. And this sounds simple enough, right? Every time that you text your friend, a carbon copy of your text will be sent to the device manufacturer as well. They collect all this data and they can train their ML models to provide us with great autocomplete and spell correct. But there is a constraint, which is privacy. Do you really want the phone manufacturer to read all your texts? And in fact, if you look back at the patent that I put up in the beginning, the word privacy is sprinkled all throughout the patent. So this is something of concern to them. So what's the basic idea, right? The basic idea is you send a randomized message. So I have my phone. I'm not going to actually send a carbon copy of the raw text messages. I'm going to send randomized messages to the phone manufacturer. The distribution from which I generate these random messages, the distribution will depend on my data, on my actual texts, but I won't just send my raw texts. So here's an example. This is me at the baby shower of my first daughter. And let's say here my text is actually an image. I texted a photo to my friends and my family. So here's the original image. I don't want to send the raw data. I'm going to send some noisified version of it. So you can just see I added more and more noise. The bottom right is the noisiest. I could add even more noise. Now here it is with like way more noise. I guess here, if you stand back, you can still kind of see that there's a head and there's a jacket, there's a collar on a jacket, but you can imagine even adding more noise than that. Okay, so this is what I send the phone manufacturer. Okay, but the phone manufacturer, ultimately, they want to know the actual data, right? Like, they're trying to train ML models. If you do that with junk, then your ML models are going to predict junk spell corrects, right? So this is not necessarily great. So the idea is the following observation. There's not just one iPhone or Android user in the world. There are millions of us, and we each, let's say there's a popular image that is being texted, like this image of me went viral for some reason. Everybody's texting around the world of this image. The phone manufacturer wants to notice that. So the idea is that each device, independent random noise, noisifies its data, and then sends that noisified data to the server, and then the server can combine, they can aggregate all these randomized messages to approximately recover information, in a way where basically they'll notice, oh, there is this image of Jelani drinking from a bottle. but they won't actually be able to tell which of the million iPhones were texting this image, right? They'll just know that this was a popular image out there without knowing anything about any individual device, what the activity of any individual device was. So the moral is, you can have each individual message look like garbage, like random noise, which protects privacy, but at the same time, in aggregate, the server can extract useful information from the crowd without knowing what any individual device did. Okay. But what exactly does privacy mean? Okay, to say that this random noise protects privacy, we have to define privacy. And in particular, maybe this example shows that it is important to have a good definition, because you don't want that you think you're private because you had a noise, but actually there's a smart algorithm that can foil you. So here, I didn't actually aggregate across a million devices. I just took a noisified image from one device, and then I ran some smart, signal processing algorithm, so-called wavelet denoising, on that single image without aggregation, on that single image to recover what you see on the right. And yes, it's not a very high quality image, but you can definitely tell that it's a person who's drinking probably a bottle, and you can see quite a lot of detail in that from a single device, right? So that's not what I want from privacy. Like, from a single device, I shouldn't be able to know what that device is doing at all, or barely at all. So you have to be careful with the definition. So the definition we're using in this talk is this popular model called local differential privacy, where device I sends a random message MI that is only weakly correlated with its data. That's what we've seen already. Almost looks like random noise, but server can extract useful knowledge in aggregate. And here's the actual definition, which I'm sure many of you probably have seen before, which is this differential privacy definition from now 16 years ago, which says the following. I say that a mechanism is differentially private if, for all devices I, and for all possible messages M, and for all data X, for all pairs of different data X and X prime. So X might be a picture of me drinking from a baby bottle, and X prime might be a picture of a cat. So just two totally different data items. The probability that I send message M, given that I have a cat as my image, versus the probability that I send message M, given that I have a picture of me drinking from a baby bottle as my image, those two probabilities should be close to each other. Ideally, if the ratio of those probabilities were the same, if the ratio were 1, it means that the distribution over my randomized message doesn't depend on my data at all, because I always output messages from the same distribution. So intuitively, that should be perfectly private, because what I'm doing has nothing to do with my data. What you learn has nothing to do with my data. So that would be the case epsilon equals 0, e to the 0 is 1. So e to the 0 is perfect privacy, meaning 0 privacy loss. But you can increase epsilon and have larger privacy loss. Okay. So informally, I said, basically, differential privacy just means the device would have been almost as likely to send the same exact message, even if their data were different. But of course, it has to depend a little bit on the data. So epsilon's not going to be 0. Otherwise, the server can't learn anything. Two regimes to keep in mind. Small epsilon, if epsilon is much less than 1, like 0.01 or something, then this e to the epsilon is roughly 1 plus epsilon. So that's a high privacy regime, low privacy loss. Then there's the large epsilon, like epsilon being 5 or 7 or something, a large constant. And actually that's what's usually deployed in practice. And you might wonder why, if I care about privacy, why would I be willing to deploy large epsilon in practice? That's bad for privacy. So the first thing to note is that there's a fundamental trade-off between utility, which is the quality of knowledge the server can learn, versus privacy, which is this privacy loss parameter, right? So in a world where the companies can do whatever they want, they would be very happy to have epsilon being infinity and guarantee no privacy, and you send your raw data and then they can learn from your data, right? But they're operating under some privacy constraints. So they want to get away with the largest epsilon they can, because it means they get the best utility they can, which means ultimately they provide better services, right? Like better autocomplete and spell correct and things like that. But it turns out that just, small epsilon turns out to incur too much utility loss to really be usable in some of these applications. So they're not willing to use epsilon being 0.01. But there is a silver lining, which is that something called shuffling improves privacy automatically. And I'm not going to really get into the details of that, but basically, between me and the phone manufacturer, there sits a third-party server, and that third-party server has only one job, which is to collect the millions of randomized messages from all the devices and apply a uniformly random permutation to them, and then forward on the uniformly randomly permuted messages to the device manufacturer, right? So what that means basically is the device manufacturer can see the histogram of messages that were sent, but doesn't actually know who sent what message. And provably, just by doing that shuffling step, you can actually, there's like a black box reduction. If your original epsilon was this, your new epsilon is much, much better. And basically, the more devices that participate in the scheme, the better the improvement to the epsilon, right? So if you have millions of iPhone users, then you can actually effectively get epsilon being 0.01, even though you design your mechanism to only have epsilon being 5. So that's why the large epsilon is what people actually usually use, or what usually gets deployed for this local model. Before going further, our particular problem for today, right? So each device holds some data xi from a domain 1 up to k, which implies a frequency histogram. F sub x is the number of devices with xi being x. And the server wants to recover f tilde that is close to f. And here I'm going to measure closeness as mean squared error, which is just the average squared difference between fx and f tilde x. Okay. So this is just the L2 norm, basically. And this, for people in the audience who are more familiar with streaming, I mean, this looks a lot like the heavy hitters problem, right? The heavy hitters problem says, I want to, given a stream over items coming from some domain, there is an actual frequency histogram f, and I want to recover an f tilde such that the L infinity norm of f minus f tilde is small, right? So here, this is not L infinity, this is L2, but it's some other error metric. I'm the one designing the mechanism. What are the things that I would like to optimize? So there are 5 bullets here, and ideally I want them all to be as small as possible. I want as small epsilon as possible. That's the privacy loss. I want a small expected mean squared error as possible. The expectation is over the random messages that are sent, right? This is a randomized protocol. I want the communication to be as small as possible. Each device will send b bits to the server. I want the server time to be fast, meaning the server collects these n messages from the n devices. Given those n messages, it has to run some algorithm to produce the approximate histogram f tilde. I want that algorithm to produce f tilde to be fast. I also want the devices to be fast to produce their messages given xi. So like xi implies some distribution over its message, and I need to sample from that distribution and output my message. That sampling has to be fast. I want that to be fast. Okay, so before I know that a lot of people in the audience maybe don't work in privacy, so maybe I'll give you a little very fast crash course. So there are some very canonical simple schemes that are already known. Maybe I'll just tell you 2 of them, and telling you them will help you appreciate, I guess, what comes next. So the first scheme is something called randomized response. So what is that mechanism? Each device sends its true item x with probability e to the epsilon times p. Otherwise, it sends a uniformly random other item, okay, so that any other item is sent with probability p. So the probability, what is p? So okay, I have to pick p so that this makes sense. So the probability that I send something is 1. So what's the probability that I send something? Well, it's e to the epsilon times p. That's the probability I send my true item, plus k minus 1 times p. So that sum has to equal 1. So p basically is determined. So we've now determined what the device does. What does the server do? The server for me is going to do a linear estimation. So what do I mean by that? So let's say it's trying to determine how many devices do I think are holding item x on the domain. So for each message mi, if mi equals x, I'll add alpha plus beta to a counter. If it does not equal x, I'll add beta to a counter. So if xi equals x, the expected contribution to the counter is, I can write it down, alpha times e epsilon p plus beta. If xi is not x, the expected contribution to this counter is alpha p plus beta, because there's still some chance that even though I don't hold x, my message randomly happens to be x, right? That happens with probability p. Right, so I want this overall to be an unbiased estimator, which means I want the expectation of the first thing to be 1, and I want the expectation of the second thing to be 0. So now I have 2 equations and 2 unknowns. The unknowns are alpha and beta. And I can solve and I can figure out what alpha and beta are. And now this is a mechanism that is 100% specified, right? We know now what the device does. We know what the server does to estimate frequencies. Okay. And the communication, we know the communication is log k bits, because ultimately I'm just sending an item from the same domain, and there are k items in the domain. So what's the error? What's the mean squared error? I'm not going to show it today, but you can calculate it. And it turns out that the error, the mean squared error, is really bad. Okay. Well, really bad compared to like other protocols that we're going to see today. So this is very fast. It's linear time server reconstruction, linear time, everything is great except really terrible error. Okay. Another simple scheme is something called subset selection. I shouldn't say it's simple. I mean, this is actually kind of it was a very important result in the area, because it was the first. It was a scheme that gets the actual optimal error. Okay, so one of a couple of schemes that do. So each device is not going to just, you're not just going to send yourself with some probability. Here's what you do instead. You're going to send a random subset of the domain of size d. D is a parameter. Okay. So what is the probability? So there are k choose d possible messages you can send, right? So for any one of those k choose d sets that you might send, what's the probability that you send it? Well, here's my scheme. If that set contains x, I'm gonna be more biased towards sending it. So I'm gonna send it with probability e to the epsilon times p. If the set does not contain my data x, I will send it with probability p. Again, what is p? Well, it's what it needs to be so that this makes sense. So the probability I send something is 1. So the number of sets that contain me is k minus 1 choose d minus 1. So the probability I send one of those sets is epsilon e to the epsilon times p times k minus 1 choose d minus 1. And the number of sets that don't contain me is k minus 1 choose d. So this sum has to be 1, which means p has to be something. How does the server estimate f tilde x? It's very similar. If x is in the ith message, I'm going to add alpha plus beta. If it's not in the ith message, I'll add beta instead. I can again write down what's my expected contribution to this counter if xi is x. What is it if xi is not x? Again, I have 2 equations and 2 unknowns. I want the first sum to be 1 and the second to be 0. I can solve alpha and beta for alpha and beta. Now that the scheme is fully determined, I can compute the expected mean squared error, and that's going to be a function of d. Remember, d was a parameter that I hadn't chosen yet. And it turns out that if you want to optimize the mean squared error, the right value of d to choose is roughly k over e to the epsilon. So if you think of epsilon as a small constant, this is k roughly. This is linear in k. So that's terrible, right? I mean, on the one hand, you can prove that this scheme gets optimal privacy loss, utility loss trade-off. Like the mean squared error you get when you analyze this is actually the best possible. And when I say the best possible, I don't just mean theta. I mean, even the constant factor is the best possible. There's just no scheme that's better than this, okay? But the thing that's terrible is like the runtimes are terrible and the communication is terrible, because I'm sending, my message is a set of size d, but d is almost the entire domain. So every one of my messages, I'm sending almost the entire dictionary, like 5% of the whole dictionary is my message, right? So that's a lot of communication, and of course, a lot of runtime for the server, because the server has to read through this, these huge messages. So those are 2, and they both fall under a meta approach. And I will say what that meta approach is, because our new scheme also falls under the meta approach. So the meta approach is as follows. Data is in the domain 1 to k. Separate from the domain, there's what I'll call message space. Message space is y, and any message that gets sent is an element of message space. So in randomized response, message space was just the same domain. In subset selection, message space was the set of all size d subsets of the domain. So message space had size k choose d. Okay. So in the meta approach, I will associate with each domain element a subset of message space called S sub x, which has size little s. And I'll also make these S sub x's so that for any 2 distinct elements of the domain, the intersection between S sub x and S sub x prime is exactly L. I will call S sub x the preferred messages for x. So I prefer to send a message in S sub x if I'm holding x. And the mechanism is, Now I have my data X. What will my message be? Well, my message will be Y with probability P if Y is not a preferred message, and probably e to the epsilon times P if Y is a preferred message, right? So randomized response and subset selection, they follow this same thing, right? In subset selection, little s was k minus 1, choose d minus 1, and randomized response, little s was 1. My preferred message was to send myself. I can again write something down because, you know, for this to make sense, I need to set p so that the probability I send a message is 1. So p is determined. It's a function of both the size of message space and little s. The server will estimate the frequency of item x in a very similar way. For each message mi, if mi is a preferred message for x, I'll add alpha plus beta to a counter. If it's not a preferred message, I'll only add beta. Again, if I'm holding x, the ith sum n had better have expectation 1. If I'm not holding x, it should have expectation 0. I could again get two linear equations with two unknowns, then I can solve them, and I get that alpha and beta are something very specific. And then now that I have my mechanism fully determined, I can try to calculate the expected mean squared error. So I need to understand the variance of my estimates for the frequencies. And there's some calculation which, you know, it doesn't, I'm not going to do it carefully because to be honest with you, I think it doesn't really matter. It's not really important for you to see the details of the calculation, just to know that it's a calculation and it's not really too complicated to do it, right? So there it is. So only focus your eyes on the very bottom here. So the point is, I can do a variance calculation and arrive at the following. The expected mean squared error is a sum of two ratios. Take it from me, the second summand, that second ratio is a lower order term. So let's ignore it. Let's just look at the first one, the one that says n times 1 plus L over S, blah, 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 blah. And the punchline is that the mean squared error increases when as L over S increases and Y over S increases. So ideally, I want these things to be small. And if we learn a lesson from subset selection, right? So now that we know this, we can look back at a scheme that is optimal, like subset selection, and try to understand how is that scheme, how did it minimize this thing? Right? How did it end up getting this thing to be small? And if you look at what subset selection did, it basically chose L over S to roughly be e to the epsilon minus 1. So the L over S canceled the e to the epsilon minus 1 in the numerator. It also chose Y over S to be roughly e to the epsilon minus 1. So added to the other e to the epsilon minus 1, it just becomes 2 times e to the epsilon minus 1. So overall, what you get is n times 1 plus 1, because that canceled. The L over S and e to the epsilon minus 1 cancels. So you get n times 1 plus 1, which is 2, times 2 times e to the epsilon minus 1 in the numerator, and you get a constant factor of 4 in the numerator. Okay, and that 4 turns out to actually be optimal. Like this exact expression is the right thing. And randomized response, it's not even just off by a constant factor. Randomized response is off by like a factor of k or something. It's just really bad. We'll see more on that soon. Okay, but anyway, so we want L over S to be small. We want Y over S to be small. Okay, we also want the communication to be small, which means we also want Y to be small. The message space should be small. It turns out that the smallest you're going to be able to get message space is the domain size. So ideally, you want the message space to be of size k, which is exactly what randomized response does. It just does it in a way that's bad for variance. So now that you know that you want Y to be small, basically what that means is you want, for a fixed, once you fix Y, you want S to be as large as possible. And for that S, you want L to be as small as possible. Okay. So this is now just purely a combinatorial design question. And known idea in combinatorics, thanks to Nogalone for pointing this out to us, is that you can get exactly this kind of behavior from finite field projective geometry. So, and it's not too complicated to explain it. I'm going to explain it in this one slide. I'm going to pick a prime Q to be roughly e to the epsilon, and I'm going to find projective points in FQ to the T, the vector space of dimension T with entries in FQ, as basically these are just non-zero vectors where I consider two vectors to be similar if they're off by only a scalar multiple. So if that's the case, I can canonicalize any vector by normalizing it by a scalar so that its first non-zero entry in the vector is a 1. Okay. So a projective point is simply a non-zero vector in fq to the t whose first non-zero entry going from left to right is a 1. The number of projective points is not hard to see. It's q to the t minus 1 over q minus 1. Why? I subtract 1. So the number of vectors is q to the t. I subtract 1 because I don't allow the 0 vector. And then for each non-zero vector, there are q minus 1 scalar multiples of it, right? Because there are q minus 1 non-zero scalars in the field. So I divide by q minus 1 to canonicalize. Okay. I will identify my domain with projective points. So I'll just I'll pick t to be, once I fix q, I'll pick t as large as I need so that there are enough projective points so that I can identify each domain element with one of them. And so now x, my domain element, is just a t-dimensional vector over fq whose first non-zero entry is a 1. It's a vector. And the preferred message set for this vector is the projective subspace orthogonal to x. That is all projective points u such that x dot u is 0 mod q. And the bottom line is if you do this, you can get the nice SL and Y we wanted. First of all, let's say you're lucky and your k is exactly of the form q to the t minus 1 over q minus 1. Then your message space has exactly size k, which is the same as randomized response. Okay, so that's good. Now, in terms of understanding what is the size of the preferred message list, what is the size of intersections, this is where it's handy to operate over subspaces in finite fields. So forget about the projective part, right? The point is, the preferred message list is a subset, is a subspace. It's a subspace of dimension t minus 1. So what's its size? It's q to the t minus 1. And then if I take two different data elements in the domain x and x prime, these are two different vectors. I have the subspace which is orthogonal to x, and I have the subspace which is orthogonal to x prime. And I look at their intersection. That's just the subspace of dimension t minus 2, which has size q to the t minus 2. And by the way, this is why it's important that I canonicalized and used projective points, because if I didn't canonicalize, x prime might just be a scalar multiple of x, in which case the intersection of these two subspaces, well, they're the same subspace because it's actually the same point up to a scalar multiple. But since I'm doing this projection, I'm guaranteed that all of these different projective subspaces are different. They're different subspaces. So I get a uniform size on their intersections. So let me write a table now of results. So there are a bunch of schemes that were known before: randomized response, subset selection. There are also things called rapport and HadamardResponse, RecursiveHadamardResponse that I didn't talk about. And then the bottom two are our new schemes. Okay. Right. So by the way, I should mention, right, like this now determines the mechanism. This falls under the meta approach. I've told you what the message space is. I've told you what the preferred message lists are. That's it. I don't need to tell you anything else, right? And it's true that all the preferred message lists have the same size because they're all subspaces of the same dimension, or projective subspaces of the same dimension, and all the intersections also have the same size. So that's it. Okay, so that's projective geometry response. Now, what was known before? Randomized response, great communication, great server time, terrible utility loss. You can see it's like n times k. If you look below at some of the other ones, there's no times k in the other ones. Rapport and subset selection are similar. Bad communication, bad server time, but optimal utility loss. PI-RAPPOR came out, that was by Kunal, that was by Vitaly Feldman and Kunal Talwar, which came out, I think last year in NeurIPS. And that had good communication, also optimal utility loss, but the server time was quadratic in K. Actually, one consequence of this work is we give a new algorithm for PI-RAPPOR server reconstruction, which is faster, but still not as fast as our new algorithm. And then you have HadamardResponse and RecursiveHadamardResponse, which have great communication, great server time, but their utility loss is off by a constant factor. And I know we as TCS people usually just, who cares about constant factors? That's in the big O. So I want to spend just a little bit of time on the slide explaining that the constant factor is actually very important. I mean, people in industry care quite a lot about this constant factor. I mean, this stuff, I mean, I'm not going to, I don't know what algorithm is running. I can't say like companies, I mean, smart people who make smartphones are actually running something. They're actually deploying some kind of private mechanism to be able to solve this problem. And, you know, what can I say about the constant factor? So the point is, normally, if you have a slow algorithm, let's say the constant factor in your algorithm in the runtime is not like the best constant factor. There are a few ways to talk about this. You could say, well, maybe if I just buy more machines, you know, like these companies, they buy millions of machines, right? So if I have like a server farm, maybe I can speed things up by parallelization. So maybe it's not so bad. I'll just spend more money on more machines if I don't have the right constant factor in my runtime. Or, you know, chips get faster, CPUs get faster. You know, I can make those kinds of arguments. But utility loss is not like that, right? So, I mean, utility loss translates directly into the error I get from training my ML models, right? Like all this stuff, whatever I learned from this frequency estimation is getting fed into something downstream to get better autocomplete. And companies, for whatever reason, I mean, companies obsess about getting good performance, like in their ML predictions, right? So if you using your phone always get the wrong thing in your autocomplete, that's going to be not pleasant. And that's not a problem here in utility loss. That's not a problem that can be fixed by just buying 1,000 more machines, right? The utility loss is an inherent property of your mechanism that the only way you can really make it get better is by changing n, where n is the number of devices out there, right? But I don't really have control over that. I can't really change n. The number of people who have iPhones is whatever it is. So I mean, that's why in deployment, some of these companies, I mean, they actually don't mind running a slightly slower algorithm if it means they get better utility loss, because that translates to better products for their customers. So anyway, projective geometry response is our new thing. It's optimal communication, log k. It's optimal utility loss. It gets the factor of 4. And if you look at the server time, it's within hitting distance of maybe HadamardResponse and RecursiveHadamardResponse, right? So it's not k log k, but it's k log k times e to the epsilon. And epsilon in practice is usually a small constant, like 5. E to the 5 is roughly 150. So it's roughly 150 times slower than HadamardResponse, which you could say, oh, that sounds like a lot, but maybe this is not actually the bottleneck in your, you know, I mean, they're doing other things. This is getting fed into ML model training or whatever else they're doing, right? So if this is, if the HadamardResponse wasn't the bottleneck in the runtime anyway, then maybe you can afford blowing it up by 150. And also, again, all these algorithms are extremely parallelizable, including ours. You can get almost linear speed up if you have P processors. So you can also, this is also the kind of thing where you can speed it up just by having more machines. If you are a little obsessed with the server time, we also give a version of our mechanism that I haven't told you exactly how it works yet, but basically it lets you trade off utility loss for server time. So instead of multiplying your server time by e to the epsilon, which is 150, you can multiply it by any prime you'd like you can multiply it by q equals 5, let's say. So your server time will blow up by a factor of 5. And then your utility loss will take a hit. It'll get a 1 over q minus 1 factor worse. So it'll get 25% worse. So instead of 4n, you'll get 5n in your utility loss, which is still better than 8n. Okay. But now your server time is only 5 times slower. We actually implemented every single algorithm on this table, ours as well as all the other ones. So this is a plot of the mean squared error for particular k and n and epsilon. The thing to note is that, look at the left curve, randomized response is so bad. It's the one, like high is bad, high is more error, more mean squared error. Randomized response is so bad that it's hard to even distinguish the other algorithms below. So let's now plot it again without randomized response. And what you can see here is, again, it's different parameters, but I mean, recursive Hadamard response and Hadamard response. Sometimes one is slightly better than the other, but they both actually run pretty similarly. So actually, what that means is the 36 in the analysis might be wrong. I'm not sure. It might be a loose constant, but it's definitely not 4. So HR and RHR are similar, but noticeably worse than some of the others. HPG5, that's our algorithm at the very bottom with Q equals 5. So it's noticeably better than HR and RHR in terms of error, but it's also worse than subset selection in PG. So subset selection is dark blue. PG is our new projective geometry mechanism. That's in teal and light blue. And if you notice, PG and SS are kind of at the bottom and they're roughly tied. More plots, they just confirm kind of what the theory says, which is that projective geometry gets basically the same error as subset selection. More plots. And we also did a timing experiment, just ran this with a domain of size roughly 3 million, epsilon being 5. We did the hybrid version of our algorithm with Q being 3, so that basically increases the error by 50%. So it makes it goes from 4 to 6. And punchline, the previous state-of-the-art algorithm in terms of error, which was faster than subset selection, better communication, it ran in more than half an hour on my machine. Our new mechanism ran in 37 seconds. The hybrid version of our algorithm ran in 6 seconds. And HadamardResponse and RecursiveHadamardResponse ran on the order of a second. So between half a second and 1.5 seconds. So, we're definitely slower than HadamardResponse, but we're, I think, within hitting distance, and we get the actual optimal error. And we're way faster than the previous state of the art that got optimal error, from half an hour down to 30-something seconds. So why is our scheme fast? So I told you what our scheme is. I didn't explain why it's fast. Again, what is our scheme? So our scheme is we identify a domain element X with a canonical two-dimensional vector with probability e to the epsilon times PS. We send a uniformly random canonical vector orthogonal to X. Else we send a uniformly random canonical vector which is not orthogonal to X. Canonical again means it's a non-zero vector whose first non-zero entry is a 1. So again, remember that to estimate the frequency of X, we need to compute this sum, which is, if I factor out the alpha, basically what I need is I need to count the following. How many devices sent a message which is orthogonal to X? So if I define a histogram Y, where Y sub U is the number of messages MI equal to U, that sum is just the sum over all canonical vectors U such that X dot U is 0 mod Q of Y sub U. Okay, that's that sum. So now I want to be able to compute all these sums for all X's simultaneously, right? There are K different values of X here. So naively, I could just do that. I could loop over all values of X. There are K of them. For each one, I could sum up over all the canonical vectors that are orthogonal to X. There are roughly K over Q of them. And my total time to compute all these K different sums would be something like K squared over e to the epsilon. So quadratic in the domain size. But I want something that's closer to linear. So I can actually do this faster using dynamic programming. So the idea is as follows. I'm going to define a function capital F, where capital F of ABZ is the sum over all U such that the length J prefix of U equals A, and the length T minus J suffix of U dotted with B is congruent to Z mod Q of Y sub U. And then the F tilde V thing, I mean, the thing that I actually want is just basically related to capital F of null comma V comma 0, right? Because at the end of the day, at the end of the day, I don't have any constraint on the prefix of U, and I want the entire U dotted with V to be 0 mod Q, right? So the length T suffix, which is everything of U, had better equal V, and dotting it with, so that will equal U, and the dot product of that with V should be 0 mod Q. It should be orthogonal to V, right? So that's what I want. I want F of null V 0. I wrote beyond the scope of today's talk. Actually, sorry, I didn't mean to say that. It's not really beyond the scope of today's talk. I should have included it, my bad. But it's not too hard to show that F satisfies a recurrence relation, and then you can use dynamic programming to do that quickly. And then you can use the usual trick with dynamic programming of like, so basically, if you look at the DP table, all the answers for a fixed value of J, right? So J here is the length of A, the length of the prefix I care about. All the values in the table for a fixed value of J only depend on the previous value of J. So I can save memory in my DP by doing bottom-up DP. And then there's one more trick. If you count like how many states and what's the total runtime of this DP, it's actually a factor Q slower than what I promised you. And you can speed up the DP by a factor of Q via basically a trick where you realize that F of ABZ is equal to F of A alpha B alpha Z for any alpha, right? Because if the suffix dot B is Z, then the suffix dot alpha B must be alpha Z mod Q. And then I can choose, I can basically only fill in the table, the DP table, where B is canonical, right? Because if B is, if I actually in my recursion cared about a B that was not canonical, I can just look up the table entry for the corresponding canonical version of B by multiplying by the appropriate value of alpha. So that's all I'll say about the DP. It's nothing, I promise you, it's nothing too deep. If you set up all the definitions right, it's a DP problem you could probably give in your undergraduate algorithms course as a homework. And in fact, you can implement the DP. So here it is actually implemented. It's not super long to implement. To be fair, there is a util package that is also in our code, which implements some of the things that the DP needs, but it's not super complicated. It's also possible to trade off utility and time. So for any prime q between 2 and e to the epsilon plus 1, you can worsen utility by roughly a 1 plus 1 over q factor. Actually, it's 1 plus 1 over q minus 1. And then speed up the runtime by an e to the epsilon over q factor. And the basic idea is you break up the universe, the domain k, into h blocks of size k over h each. Each device first basically does randomized response to reveal its true block with some probability, and then do the projective geometry mechanism inside that block if it chooses to reveal it. Otherwise, if it chooses to not reveal its true block, it just sends a totally random message. And we call this scheme hybrid projective geometry response. So it's like a hybrid between randomized response and the projective geometry mechanism that we just described. And it gives some kind of trade-off between utility loss and runtime. Faster runtime again, because randomized response is fast. And also you're basically doing projective geometry over a smaller domain, so it's faster. Open problems, I guess the first one is not really a theory problem, but like, is there a chance that maybe this thing will get deployed on actual smartphones? To be determined. One thing that I mentioned it, but I didn't really focus on it, but it's important, is remember, I identified my domain with projective points over in fq to the t, which means that I assumed k was of the form q to the t minus 1 over q minus 1. What if it's not of that form? I basically have to round up t to the next integer so that I have enough points for my domain size. But then that means I might end up having to work over a domain that's a factor q larger than what I really want to work over. And remember, q is roughly e to the epsilon, which practically is like 150, which means I'm working over a domain that's about 100 times larger than I really wanted to, just because of this rounding issue, which means the runtime of my server reconstruction is going to be 100 times slower than I really want it to be. So if you could come up with a combinatorial construction of these like preferred message lists that work for all values of k instead of just k of a certain form, or at least all values of k that are powers of 2, or like denser so that the penalty for rounding up is not as large, I think that would be interesting. Also, as I mentioned, finding an approximate histogram such that f minus f tilde is small is basically the heavy hitters problem. I mean, heavy hitters and streaming is usually it's like the norm you care about is L infinity, but this is related to the heavy hitters problem anyway. And what we know, even in the differentially private setting, is that there are sublinear on the server side, time heavy hitters algorithms with the optimal constant and the error. Okay. So can you get sublinear time algorithms with the optimal, so we know that there are sublinear time heavy hitters algorithms in the local DP setting, but everything in those papers are all like big O. Okay. So can you get sublinear time heavy hitters algorithms that actually have the optimal constants in the error and the reconstruction error? So I think that would be maybe the next logical step. And that's all I have for you today. So I'm happy to take questions.